Chapter 1.6.2 Persistent Volumes. This document provides an overview of persistent volumes in Kubernetes and suggests familiarity with volumes, storage classes, and volume attributes classes for better understanding. Introduction. Managing storage in a cluster is a separate challenge from managing compute instances. The persistent volume subsystem simplifies the process by providing an API that separates the details of storage provision from its consumption. This system introduces two new API resources, Persistent Volume, PV, and Persistent Volume Claim, PVC. A PV is a piece of cluster storage provisioned by an administrator or dynamically using storage classes. It functions as a volume plugin with a lifecycle independent of any pod using it. On the other hand, a PVC is a user's request for storage, similar to a pod's request for resources. The PVC specifies size and access modes for storage, while the PV abstracts the implementation details such as NFS, IC, or cloud-specific systems. To meet different storage requirements, administrators can offer various PVs with different properties via the storage class resource, without exposing users to the underlying implementation details. This system benefits users and administrators in efficiently managing storage resources within a cluster. Lifecycle of a volume and claim. Persistent volumes, PVs, are resources within a cluster, while persistent volume claims, PVCs, are requests for those resources and serve as claim checks to access the resource. The lifecycle of the interaction between PVs and PVCs includes provisioning, binding, and using the resources. Provisioning of PVs can be done statically by a cluster administrator creating PVs with details of available storage for cluster users, or dynamically when no static PVs match a user's claim, and the cluster provisions a volume based on specified storage classes. Binding occurs when a PV is matched with a PVC, binding them together in a one-to-one mapping using ClaimRef. Once bound, the relationship between a PVC and PV is exclusive and remains until the user no longer needs it. When a user is done with a volume, they can delete the PVC object from the API to allow reclamation of the resource. The reclaim policy for a persistent volume determines what happens to the volume after it is released, with options for retain, recycle, or delete. Retain allows for manual reclamation of the resource, where the PV still exists after the PVC is deleted, but the data remains on the volume until manually cleaned up. Delete removes both the PV object from Kubernetes and the associated storage asset in the external infrastructure. The recycle policy is deprecated in favor of dynamic provisioning. A feature called Storage Object in Use Protection ensures that PVs and PVCs in active use by pods are not removed immediately to prevent data loss. If a PVC in active use is deleted, it is postponed until it is no longer actively used, while deleting a PV bound to a PVC is also postponed until it is no longer bound. Finalizers are added to PVCs and PVs to indicate protection status. Expanding persistent volume claims is enabled by default in Kubernetes v1.24 and supports various types of volumes, but can only be done if the storage class's allow volume expansion field is set to true. Volume expansion can trigger the underlying persistent volume to be resized without the need to create a new one. Resizing a volume containing a file system is only possible for certain file systems when a pod is using the PVC in read-write mode. Recovering from failure when expanding volumes can be done manually with cluster administrator access by requesting expansion to a smaller size or marking the PV with a retain reclaim policy. Recovery from failing PVC expansion by users is also available as an alpha feature in Kubernetes 1.2.3. Users can retry expansion with a smaller proposed size if the previous attempt failed due to capacity constraints. Overall, the life cycle of PVs and PVCs in a Kubernetes cluster involves provisioning, binding, using, and reclaiming the resources while ensuring data integrity and flexibility for users and administrators. Types of persistent volumes. Persistent volume types in Kubernetes are implemented as plugins, with supported plugins including CSI, FC, HostPath, IC, Local, and NFS. Deprecated persistent volume types are still available, but it is recommended to install corresponding CSI drivers if using those types, except for Flex Volume, CephFS, and RBD. Some of the deprecated types include AOS Elastic Block Store, Azure Disk, Azure File, Cinder, Flex Volume, GC Persistent Disk, Portworx Volume, and vSphere Volume. Older versions of Kubernetes supported in-tree persistent volume types such as CephFS, Flocker, Photon Persistent Disk, Quobyte, RBD, Scale.io, and StorageOS, but these are no longer available starting v1.15 or later. It is important to consider these plugin types when setting up persistent volumes in Kubernetes and to ensure proper migration if using deprecated types. Persistent volumes. Persistent volumes, PVs, in Kubernetes contain a specification and status. The name of a PV must be a valid DNS subdomain name. Helper programs may be needed to consume a persistent volume within a cluster. The capacity of a PV is set using the capacity attribute, with storage size being the only resource that can currently be set or requested. Future attributes may include IOPS and throughput. Kubernetes supports two volume modes for PVs, file system and block. File system is the default mode and is used when the volume mode parameter is omitted. A volume with volume mode, file system is mounted into pods in a directory. If the volume is backed by a block device, Kubernetes will create a file system on the device before mounting it. The volume mode can also be set to block, allowing a volume to be presented as a raw block device to a pod. PVs can have different access modes, including read-write once, read-only many, and read-write many. The read-write once pod access mode, introduced in Kubernetes v1.29, allows a volume to be mounted as read-write by a single pod. In some cases, the volume access modes constrain where a PV can be mounted, but they do not enforce write protection once the storage has been mounted. A PV can have a class specified by the storage class name attribute, with PVs of a particular class only being bound to PVCs requesting that class. The volume beta annotation volume.beta.kubernetes.io/storage class is still supported, but will be deprecated in a future Kubernetes release. Reclaim policies for PVs include retain, recycle, and delete, with only NFS and HostPath types supporting recycling in Kubernetes 1.31. Kubernetes administrators can specify mount options for persistent volumes for certain volume types, such as Azure File, CephFS, and NFS. Mount options are not validated and may cause the mount to fail if invalid. Node affinity can be set for a PV to define constraints on which nodes the volume can be accessed from. Phases of a PV include available, bound, released, and failed, with a new feature in Kubernetes v1.31 allowing for the last phase transition time field to record the timestamp of when the volume last transitioned its phase. In summary, persistent volumes in Kubernetes have specifications and statuses with different volume modes, access modes, classes, reclaim policies, mount options, node affinity, and phases. Administrators can use various attributes and options to configure and manage persistent volumes within a Kubernetes cluster, allowing for more control over storage resources. Persistent volume claims. Persistent volume claims (PVCs) are used in Kubernetes to request storage resources with specific specifications and status. The name of a PVC must be a valid DNS subdomain name. Claims use the same conventions as volumes for requesting storage with specific access modes and volume modes, either as a file system or block device. They can also request specific quantities of storage resources and specify a label selector to filter the set of volumes that can be bound to the claim. A PVC can request a particular storage class by specifying the name of a storage class using the attribute storage class name. Only PVs of the requested class can be bound to the PVC. If a PVC doesn't request a class, it can be interpreted as requesting a PV with no class or a default storage class. The Default Storage Class Admission plugin can specify a default storage class for PVCs with no storage class name, and the cluster will respond accordingly. Retroactive Default Storage Class Assignment allows for the creation of a PVC without specifying a storage class name, even when no default storage class exists. When a default storage class becomes available, existing PVCs without a storage class name will be updated to match the new default. PVCs with an empty value for storage class name will also be updated, except for PVCs where storage class name is already set to. Administrators can change default storage classes by removing the old one first, allowing PVCs without storage class name to not have any default temporarily, and then updating them through retroactive default storage class assignment. Overall, PVCs in Kubernetes can request storage with specific specifications, access modes, volume modes, resources, selectors, and storage classes. Retroactive default storage class assignment allows for the updating of existing PVCs to match a newly configured default storage class to ensure proper binding to PVs with the correct settings. Claims as volumes. Pods access storage by using claims as volumes, which must exist in the same namespace. The cluster locates the claim in the pod's namespace and uses it to retrieve the persistent volume. The volume is then mounted to the host and the pod. Persistent volumes are exclusive, so claims with many modes can only be mounted within one namespace. Persistent volumes typed as host path use a file or directory on the node for storage. Raw block volume support. In Kubernetes v1.18, several volume plugins now support raw block volumes, including dynamic provisioning where applicable. The supported plugins include CSI-FC, ISI, Local Volume, OpenStack Cinder, RBD deprecated, RBD Ceph block device deprecated, vSphere volume, persistent volume using a raw block volume, persistent volume claim requesting a raw block volume, and pod specification adding raw block device path in container. If a user requests a raw block volume using the volume mode field in the persistent volume claim spec, the binding rules have been updated to consider this mode. A table is provided to help users and administrators specify and bind raw block devices. Note that only statically provisioned volumes are supported for alpha release. Admins should consider these values when working with raw block devices. Volume snapshot and restore volume from snapshot support. Kubernetes v1.20 introduces stable support for volume snapshots, which are now only compatible with out-of-tree CSI volume plugins. In-tree volume plugins are deprecated, and users can refer to the volume plugin FAQ for more information on this change. One can create a persistent volume claim from a volume snapshot. Volume cloning. Volume cloning for CSI volume plugins allows for creating persistent volume claims from existing PVCs. Volume populators and data sources. In Kubernetes v1.24 beta, a new feature has been introduced that supports custom volume populators. To use this feature, the AnyVolume data source feature gate must be enabled for the Kube API server and Kube controller manager. Volume populators utilize the data source ref field in the PVC spec, allowing references to any object in the same namespace except for core objects other than PVCs. It is recommended to use data source ref over data source in clusters with the feature gate enabled. Cross-namespace data sources. In Kubernetes v1.26 Alpha, there is support for cross-namespace volume data sources. To utilize this feature, the AnyVolume data source and cross-namespace volume data source feature gates must be enabled for the Kube API server, Kube Controller Manager, and CSI Provisioner. Enabling cross-namespace volume data source allows for specifying a namespace in the data source ref field. It is important to note that reference grant from the Gateway API must be extended to the Kubernetes cluster before this feature can be used effectively. Data source references. The data source ref field in Kubernetes behaves similarly to the data source field, where if one is specified and the other is not, both fields will have the same value. Both fields cannot be changed after creation, and attempting to specify different values for them will result in a validation error. The data source ref field allows for different types of objects, whereas the data source field only allows PVCs and volume snapshots. When the cross-namespace volume data source feature is enabled, the data source field only allows local objects, while the data source ref field allows objects in any namespace. It is recommended to use the data source ref field on clusters with this feature enabled, and the data source field on those without. The duplicated values with different semantics exist for backwards compatibility. Volume populators are controllers that can create non-empty volumes based on a custom resource. A populated volume is created by referring to a custom resource using the data source ref field. External controllers should generate events on the PVC to provide feedback on the status of the creation. Installing the Alpha Volume Data Source Validator controller can help generate warnings if a PVC cannot be created due to missing components. Additionally, creating a reference grant allows the namespace owner to accept the reference when specifying a cross-namespace volume data source using the data source ref field. Writing portable configuration. For configuration templates or examples that require persistent storage on a variety of clusters, it is advisable to include persistent volume claim objects in the configuration bundle rather than persistent volume objects. This is because users may not have the necessary permissions to create persistent volumes. By allowing users to input a storage class name when instantiating the template, the PVC will match the correct storage class if storage classes are enabled by the admin. If no storage class name is provided, a PV will be automatically provisioned using the default storage class in the cluster. It is important to monitor for PVCs not getting bound, as this could indicate a lack of dynamic storage support or a missing storage system in the cluster.